Okay, so since I think the others are joining late, I think I need to maximize the time. So basically, you just have to go to the recording to see the um, this part of the discussion. So for today, I want to finish the coverage on the basics of probability, particularly discuss the things about joint distribution and lastly, Bayes rule. So I know that the topics that we're discussing are really complicated and somewhat counterintuitive, and this is not typically something that you would expect from a boot camp because usually boot camps are applied in nature. They focus more on the application, but well, it's not good if we'll just proceed with the application of these concepts without even discussing the root, the main foundation on which these methods are built on top of. So yeah, for the first part, let's do a quick recapitulation of what we were able to discuss for this week. I'll be sharing my screen now. Okay, so I hope it's sharing now. So again, probability is basically a study of uncertainty. So we just try to make sense of the things around us. We want to understand how we can predict that, or how can we measure that something will happen, the odds of that something would happen. There are so many applications to this, such as in machine learning, if you want to develop a system, an automated system, and teach your that system to identify a certain thing, like for example, identify say a person or an animal, or for example with Tesla's autopilot, they were able to identify if what's in front of them, right? They were able to somehow see with some degree of uncertainty what's in front of them. So based on that, they slow down. The system is um, programmed to do those safety maneuvers based on all of them are based on probability and um, yeah. Let's see. Yep. Welcome to the meeting, Jeff. So you're the first
How's it going,
participant.
Jeff?
Yeah. I'm doing great. How are you?
Give me a sec. I'm just setting up my bike. I'm
Okay.
good. How are you?
Okay. Yeah. So basically, I think we're on the last leg of the discussion about probability, particularly the basic concepts. I'll try to finish the coverage for the two remaining topics today, and then proceed with a set of new ones on Saturday. So yeah, how's the lab? I think John was able to give you
It was pretty good. It was pretty good. Pretty
informative,
good. Pretty
yeah,
information.
hands-on experience on some of the parametric and non-parametric methods.
It's kind of funny because I was talking to a friend yesterday, and
Mm,
like she actually does data science, and it's kind of interesting because she was telling me something. I guess maybe this
Jeff,
might be like
your volume is low.
uh, oh yeah, like I was talking to a friend, and
Mm.
she's a data scientist, and she was saying something about like there's two school of thoughts. One is called
Mm.
like Bayes.
Oh
One
yeah,
is called
Bayesian
something. So
frequentist.
apparently like yeah, like apparently like she's saying like Bayes like actually thinks like like I don't know, like what we're doing, like the hypothesis, like it like it's not like it's not rejecting it, but it's just saying that like it's like not, it doesn't completely mean that it's like we can come to conclusion or something like that from the p value or something. Like it's kind
Yeah.
of interesting. So something about like we're like, oh, it's like I don't, I like, I was like, well, how do you guys like, you know, how does Bayes kind of think about, you know, things like, but maybe it's just that like maybe they're just more conservative or something.
Mm.
Like,
Yeah, with the Bayesian approach, basically you're adjusting your estimates, your probabilities, or anyhow you call it, based on new information coming in. So whenever new information comes in, your estimates would be adjusted. Your estimates of the probabilities of an event would also be adjusted. So we have an example of that. Uh, Bayesian statistics is one of, well, we only have two, with the frequentist approach and the Bayesian approach. Compared with the frequentist approach, Bayesian is not that famous. So you can either be a frequentist statistician or a Bayesian statistician. But there are also benefits as well with Bayesian statistics. So yeah, we'll have a chance to um, sort of get an idea on what do you mean by the Bayes rule, which is the foundation of Bayesian statistics. But the simplest idea, the simplest way I can explain it is whenever new information comes in, like the occurrence of some events, your estimates will be adjusted as well. So like our example about the rain, if they say the chance of raining today is 30%, but it rained yesterday, so like the every same day of the month has a probability of raining, say 30%, but it rained yesterday. So that 30% would then be adjusted by the occurrence of the event that it rained yesterday. So there would be an update to that prior probability. So any new information such as that comes in, the prior probability would be adjusted. So this is also what they're doing with clinical trials. Let's say in my example that I'll be discussing later is, suppose that a person was diagnosed with a disease, positive with a disease such as COVID, and your test kit has a true positivity rate of 99% and a false positivity rate of say 5%. Now, given that the person was diagnosed with a um, positive given that the person was diagnosed as positive, what is the probability that he is actually positive? He is a true positive. Okay, so we'll be discussing the answer to that later. You might be think you mentioned that it's already 99%, right? But it's not. It's kind of counterintuitive in a sense that um the prior probability would be adjusted, either it would be increased or decreased based on the idea that um, a certain event has happened. So that's the idea of Bayesian statistics, Bayesian probability. In its early conception, people can't really believe that Bayesian statistics is true. Well, mathematically it is. It is mathematically on point, but it is very counterintuitive in a sense that your prior probability could significantly decrease by the existence of um, an event that is related to it. So
oh, interesting.
yeah, we'll be considering some examples for that. Okay, to make things clear, I think just talking about it is not that efficient, I would say, and not that effective. So we have to look into the mathematics deeply and try to see what we're referring to as like updating of the probabilities based on the occurrence of another event. So anyway, yeah, let's move forward. So we have defined probability during the early part of this lecture, and we have looked into naive probability and probabilistic events. So I hope you can still remember the difference between the two. And one of the most important part of our previous lectures would be this, the three axioms of probability. Should always remember that the bounds for a valid probability would be between 0 and 1 inclusive. The lowest it could possibly go would be 0, and the highest would be 1. Because it doesn't make any sense to go lower than 0 and to go higher than 1. Okay? Because 0 is an impossible event, and 1 is a sure event. So you cannot say overstate. Okay? Uh, you cannot go over that those figures. And we have this sum of probabilities, right? Um, all of the probabilities of the possible events in your event space, like tossing a coin, you have a 1/2 chance or a 50% chance of getting a head, and also a 50% chance of getting a tail. When you sum those up, it will be equal to 100%, or um, another way of saying it is you have a probability of 1 if you get the sum of those two events when you do an experiment of tossing a coin. And now we have here an extension of that axiom, that is the complement of an event, or the probability that the event will not happen is just 1 subtracted by the probability of it happening. So if the probability that you will get a tail is 50%, then 1 minus 50% is your probability of not getting a tail, right? So you have that P of A bar, which is read as probability of A complement. Sometimes they write it with superscript C, but oftentimes you would see that they people would be using bar. Others also use negation. If you can remember the logical operation for negation, it's like a negative sign with a downward line, something like this. You can find that in some books. So something like this. So that is just similar or equivalent to a bar, and that is just equivalent to a complement. Oh, it does that thing again. Um, Let me fix that. So all of this is just pertaining to the same thing. That is the complement. What is the probability that A will not happen? Okay, you can get that by subtracting 1, because you know from axiom 2 that the total should be 1. So if you subtract, if you are only speaking of one event and you want to identify its probability of not happening, then you just subtract that 1. And there you go, you'll get the complement. So this must be understood by heart. Okay, you have to remember it, that when you're working with probability, these are the three most important axioms. Okay, but there are tons of this. If you really want to be a master of probability, like on like on a different level, there are, I think, around close to 200 axioms that you have to really master. But of course, in the applied sense, you don't need to know all of them. This one could be like a consequence of the other. Like for example, um, the thing that we'll be discussing later, you can derive the base rule by looking into this different principles and axioms that we talked about. Hi Grace, welcome to the meeting. How are you? Okay, I see that you're raising your virtual hand. Okay. How
Hi.
was?
Yes, sorry. I'm good.
Yep.
How are you?
Are you at work today or not?
No, I made it home. I just had to stop by a store pick up something before they closed at 6.
Oh,
So,
okay. All
sorry
good,
I'm
all good.
late.
No worries. I totally understand. It's really tough to have a class after work. I've been into that situation since I started university life. It's really
Yeah,
tough.
and like I like knew the idea of the time commitment, but I was like,
Yes,
it can't be that hard because there's people who work full time, go
yes.
to school part time, and then they parent, which just sounds like absolutely insane to me. Sounds like it can't be that hard, but it is really taking up, it's actually a
Yeah,
really big commitment. So
it's a big
I have to
commitment.
like check my
And
attitude and do
mm,
my work and get
it,
disciplined. So
yeah, it is also a good thing that we see those kinds of situation because sometimes we get too narrow-minded if we just stick with like the common in our like in our place. That's why. Are you familiar with? I think well, R.I.P. to him. But are you familiar with this person? What's the name of that? A traveler and a chef. Parts Unknown is his.
Bourdain, Anthony Bourdain.
Yes, Anthony Bourdain. I love Anthony Bourdain. He has this mentality that he wanted to see the how different people live, different situations. So it kind of made his view about life different. But of course, yeah, I think he died of suicide, right? So I think there was a depression issue. But anyway, it's good that we have that we have that internalization reflection about our sometimes privileges, right? And it helps us regulate ourselves. So I think that's very good. And I love to see that kind of thing from people. So anyway, moving forward here. So we're just doing a recapitulation. I know that this is something that's very difficult to process. You might be thinking that you're just wasting your time going over these topics, but in reality it's not. The moment you really commit to analytics, and if you want to advance your career to not only being a data analyst but also be a data scientist, these things are indispensable. You have to be masters of probability. So at least now I'm introducing to you some of the things. This is not all. This is a very complex and broad subject, and they are intertwined with others. Um, at least by now, you have a valid expectation of what you need to go through in order to level up. So moving forward, we discussed this different types of probabilities. Marginal. So if you have a die, what would be the marginal probability of like getting a specific side? That would be uh, naive probabilis probability, right? It's part over the total. So you have that event on your numerator, which is like one event out of the six. So you'll get a probability of one out of six. So this is the when we think of probability, I think this is the first one that comes to our mind, like the marginal probability. And we also have conditional probability. So conditional probability is something new, I guess, because it is understandable. It's not hard to think that the probability of an event is affected by other events, right? The probability that you will get a high salary is dependent on your skills, right? If you're highly skilled, then the probability of you getting a higher paying job would be higher. It's also dependent on your location. For example, even though like you're highly skilled, but you're in a location that has, in terms of economy, still developing, like in my country's case, the opportunity would be lesser as compared to the developed ones. So in order for you to somehow increase your pay, would be either to look for opportunities from the developed ones. So that's why we have so many what we call OFWs, or overseas Filipino workers, is because um, the, the 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 probability of them getting a higher paying job relative to what they can get from home would be much higher, right? And it gives so many advantages as well as disadvantages, for any country that has that same setup. Are you familiar with brain drain? The concept of brain drain, guys?
Can you say it again?
Brain drain, brain as in
Brain drain.
brain drain. Like, it is a common observation from developing countries that they're highly skilled, highly intelligent, highly educative, or educated individuals are moving out of the country to work for like companies in the developed ones. So you would see talents moving out of the country. That's why those developing countries have harder time to develop themselves, is because of that. People
I've
tend to
never
look
heard of
for
that
opportunities.
term. Yeah.
Yeah, it's brain drain. It's a common um, observation with developing countries. So this developed countries such as the USA, um, Britain, and um, other countries, they have the leverage. They have the leverage that they can offer like a better to opportunities to these people, so they can easily get that talent that they need. Even for example, nurses in the US, I think Filipino nurses are very in demand. So they try to um, get more of them, right? However,
There's
it's
it's
also
so many. It's synonymous with Filipinos. But what I'm seeing on like a Facebook groups is
mm,
there's a lot of teachers being brought over,
yeah, even
like
teachers, yeah.
school teachers, English teachers, so much from the Philippines because here in the States they don't want to pay teachers. So that's what's
It,
happening.
it's also a challenge for you locals, for you that are in there, Grace, because there would be more competition, and these people coming from, say, Philippines, they are, um in terms of salary, they would grab even like the minimum that you would normally offer to the same role. So if you compare, okay, I'll be offering the same to a local, then probably they would reject it, right? Because it's low relative to the standard in your country. But with this immigrants, I should say in general, they would grab that. So there would be a competition. So you really need to increase your skills, your level of um, uh, knowledge, or in general skills to really compete and get your ideal salary. It's normal. It's normal for a capitalist setup. That's how the setup works. The government can do policies to somehow restrict, but it would it would also have negative impact. At the end of the day, the system actually returns to the mean, or returns to normal after some time that a policy has been done by the government. It's just how the system works. So yeah, we it's just a conditional probability. So many events are associated with other events that it's sometimes impossible to just use marginal probabilities. If you just if you just think about marginal probabilities, then you're just thinking about enclosed system, which are not really, in most cases, realistic, right? So let's move forward. We have discussed this too, and what we are left with is this third type, which is joint probability. So with joint probability, it's just straightforward twist on marginal. So suppose you're tossing two dice and you want to ask, what is the probability that I observe a 1 on the first die and 2 on the second die? So we'll be discussing that. How can we compute? But basically, joint probability from the name itself, it's the joint odds. Okay, so you have multiple events as compared to marginal probability that you're only looking at one event. With joint probability, you are looking at the probabilities of more than one event. Okay, at least two events. And it's different with conditional probability because with conditional probability, you have that premise that those two events are related with each other. That is, the occurrence of one event actually affects the probability that the other event would occur. Okay, but with joint probability, there's a um, there's a thing that the two events could be independent from each other. So if they're independent, as you know, we have seen that in the previous lecture that the conditional probability would just be um, uh, inexistent, right? If say probability of A given B has occurred and you know you know that A and B are independent from each other, then basically you're just looking for the probability of A. Can you remember that? So let me put that into writing in case that you forgot. Oh, I can't. Okay, there we go. I want to change the color of this. I want black. So probability of A given B is just equal to probability of A if they are independent from each other. In short, well, um, not in short, but it means that since they are independent, B has no effect on the probability that A will happen. It's like um, what is the probability that you will pass this course given that Trump won the election? So you could think of, oh, okay, it doesn't make sense. Those are independent events. They have nothing to do with it. They have nothing to do with each other. So um, B has no effect on A. So it's just equal to just look for what is the probability of A if A refers to the event that you will pass the course. Okay. So with joint probability, well, it's a completely different thing because, as we will see later, it's somehow counterintuitive, but it would be clearer if we look into it in the perspective of marginal probabilities. Okay, so it's perfectly fine to do that. Look first at the marginal probability of the first event, then look into the marginal probability of the other event. If they are independent, but if they are not independent, if they're conditioned, then there would be difference. You cannot just look into the marginal probabilities and say that the corresponding probabilities would be the same if you just look at them piece by piece. So operations, so we can add, we can multiply probabilities. Here we have the union, which is basically what is the probability that A or B will happen, right? What is the probability of A or B? So that is equal to probability of A plus probability of B minus the probability of A and B. Now, if they are independent, meaning there's no intersection between A and B, then it is just the sum of their marginal probabilities, right? This will be just equal to A null or zero. It will just be cancelled, and you'll be left with the marginal probabilities of A and B, which is intuitive. It's intuitive to say that um, if you want to know the probability of either A or B, and they are independent from each other, it's just equal to just summing up their individual probabilities. That is the total probability of observing both of the event or both of the events. It's very intuitive. But um, what do we mean by probability of A intersection B, right? So as I said earlier, it is just the commonality. So if you have two sets of events, two event space or event spaces, and say both of them contains two, then that would be the commonality, and that would be equivalent to um, this intersection between event spaces A and B. Because the A and B could consist of multiple sub-events, right? I think we had this example before, right? If we have these two sets of odd numbers from 1 to 10 and set of even numbers from 1 to 10 also. Now, if you would ask what is the union between the two, then that would be just the sum. You combine all of that together, right? But if you would be asking for the intersection, there's no intersection between the two. There's no number that is both odd and even. So there would be a disconnect between the two event spaces, and therefore the probability associated to that would be a null set or zero. Now, if it's the case that such that we're not looking into specifically odds and evens, but something that looks like this, maybe some value 3 here that is existing both in event space A and event space B, then we say that the intersection would be that 3. Okay, that would be in terms of um, naive probability 3 out of 5, or sorry, 1 out of 5. The probability of A and B would be 3, which is equal to 1 out of 5. Probability of obtaining 3, okay, would be 1 out of 5, referring to A and B. Okay, referring to their intersection. So in this case, you would be needing to subtract that probability that you observed in here, because if not, then you would go over 1. Okay, if you don't subtract that intersection between the two event spaces, then you would observe that you would violate the first axiom of probability, right? Because there would be replication in a sense. So let me just clean this up because this one, I need to delete this one. Oh, it doesn't allow me to delete that. This would work. It's very messy. Okay. So are you still following, guys? The idea. Why is it always doing that? I may just want to use my Epic Pen instead because it always does that. Any questions, guys? Anything that you want to clarify, or maybe you need a proof of something? No, no. Okay, so Let's go back to the first action, and I want to show to you why do you need to subtract the probability of A intersection B. So if we go back here, the first assumption tells us that you cannot go over 1 for a valid probability, right? Now, let's see what happens if we don't subtract the intersection, right? So let's see that. So I'll be using the idea on this part right here, okay? This A intersection B. So I'll be opening a paint so that I can start with a fresh canvas. I don't want to confuse you with so many scribbles and stuffs. So I'll be using that. So we have event space for A, which is equal to 1, 2, 3. Okay. This is supposed to be a curly bracket, but it's quite difficult to actually write it using the mouse. So with B, we have 3, 4, 5. Now we'll be defining the universal set here, right? The universal set would be 1, 2, 3, 4, 5, right? So with the universal set, we'll not be replicating 3 in here because we want to be to have to have each of the events unique. So if we will ask what is the probability of A, that would be the number of events in A, which is 3, divided by the total, which is 5. And what is the probability of B? That would also be 3 out of 5. Now, what would be probability of A union B? Again, this example, we will not be considering the subtraction of the intersection. So it would now be 3 over 5 plus 3 over 5. So we have the common denominator, so we can easily add the numerators up, right? So it will be left with 6 over 5, which is greater than 1, right? This is greater than 1. And it violates the first axiom of probability that we talked about earlier, that it should not a valid probability must not go over 1. So if we subtract the intersection, that's where we will get the valid probability. That's where we will be able to satisfy both axiom 1 and axiom 2 of probability. That is, for the total probabilities in the event space, in the universal event space, it must be equal to 1. Okay, and for a valid probability, it should be at most 1. So do you get the point, guys, of why we have to subtract the intersection there? So you can think of it in the sense of sets, that you don't want any replicates. You don't want any replication when you combine them together through the union. But if they're independent, just like in this example, then there's no reason for you to reduce it, because their individual marginal probabilities, the sum of those would be just be equal to 1, right? This probability of O would be 1 out of say 5 out of 10. This is 5 out of 10, right? This is 5 out of 10, and the probability of E would also be 5 out of 10. If you get that, it will just be this. If they are disjoint or mutually exclusive, independent from each other, you'll get a total probability of 1. Do you follow, right?
I have a question.
Mm.
So with the 6 out of 5, with the probability of a 3 and then a 5, I think, right? Or of the dice. And then minus the intersectionality. What is that numerical value?
Yeah, we can compute for that, right? So let's see. Let's continue with how can I go back to seeing the thing that we had earlier? So we have this case now, which is totally incorrect. Now let's see the version in which we have a correct one. Um, I'll just delete this part right here because we have the top all everything at the top as correct. So for this one, we would be needing to define the probability of A intersection B. And what do you think is the probability of A intersection B? Can you remember our definition of A intersection B? Because it's important that we know this definition because that would be the value assigned to it. Anyone? So actually, we've gone through it. We said last meeting that the intersection just means the product, right? The product. Where is it? Yeah, there we go. So we defined A intersection B as just the product of A and B. And what do you think would be the product of that? If we go back to our computation earlier, sorry for the noise. So if P of A intersection B is just the product of the individual probabilities, individual marginal probabilities, then it is just equal to 3 over 5 times 3 over 5. And what do we have there? It would be 9 out of 25. So this is the one that we need to subtract to the sum of this. So getting the sum of this would just be equal to the probability of A union B would just be equal to the sum. So 3, this has common denominator, so that would be 6 out of 5 minus 9 over 25. And you know the drill here. You just have to find the lowest common denominator, and in this case, the lowest common denominator is 25. So we need to multiply this value by 5, the numerator, both the numerator and the denominator by 5. So this is just basic mathematics. We'll just get 30 over there over 25, right? So that we can subtract 9 out of 25, and we'll be left with, let me just delete this part so that we have, oh, why is not, um, why is that deleting the thing? Anyway, I'll just write it at the top. Again, I apologize for a very messy canvas, but let me proceed with the computation here. So that would be 30 minus 9, so we have 21 out of 25. And that is equivalent. I will not do the manual conversion, but it's just easy to do that. We'll just need to divide 21 by 25, but let me use technology. So that is equal to 84%. So mechanically, this is how you would do it. But of course, there's no reason for you to actually do that on your job. It would not. I don't think any job would ask you to do that aside from teaching, aside from university stuff. But this is how you do it. This is what we meant by subtracting the intersection, which is synonymous to saying the product of the marginal probabilities to the sum of the marginal probabilities to get the union. Okay, Grace, did I answer your question about this?
Yeah, yeah, yeah.
Okay. So I'm not. I'm just showing you this because I want you to be familiar with the navigation with the manual process. But again, um, you'll not be doing this in this exact actual process. Okay. exact actual way, but you need the principles that we have applied here to understand deeply the following topics, like the base rule, how we can um, say
Mm.
derive that formula. Okay, but we'll be focusing on, okay, so where do you use this, right? Where do you use this? So say if you want to um, get the sum of probabilities, the total probabilities of two events, and um, they are related by like a common outcome, then you first need to subtract that common outcome to the sum of the two events that you're computing the probability of. So in that sense, you'll be eliminating the redundancies that that event is appearing in the event space of the first event and also in the second event. And you will not have a weird total probability that could go over one. So if you don't do that, then you might be overestimating your probabilities. Okay, you are overestimating that. Now moving forward, okay, moving forward to that, um, this is very messy, and I'm extremely sorry. I think I have to clean this up before I post it in in Canvas. Okay, we've gone through independent probabilities, and you know the gist of this. And it's very intuitive. It's easy to follow that, yeah, an event or two events, if they are independent from each other, then you just have to get the marginal probabilities, right? If you're looking for A, then just look for the marginal probability of A. You don't have to know the probability of B or the influence of the occurrence of B to A if they are independent. There's no reason for you to do that. Now, that works in both ways. If A is independent to B, it also follows that B is independent of A, I should say. Okay, so it's in a sense, in mathematics, you call that commutativity, right? It's commutative even if you change the position. Okay, you commute the position of um, the the events, it would still be the same. You just get the marginal probabilities. If you're asking for the probability of B given A has occurred, and they are independent because you know that A is independent of B, then it follows that you just need the probability of B is also independent of A, as it implies. Now, that's not always the case. I mean, in nature, most of the events are intertwined. It's like a web. What you do today affects what you do now affects so many things, succeeding things. Say if you decided to drink coffee this morning, then you will have more energy. If you did not decide, if you did not drink coffee, then you will have less energy. If you're not drinking coffee, you can think of like Grace. If she did not go to the shop, then she will not get the supplies that she needs. So there are chains of events, and there are multiple futures, as they say. So those futures are identified by the events that you do that you do now. So they say, this is a weird thing. They say that those futures are actually happening simultaneously in our universe. Whether, for example, I have my phone in here, there's also another universe in which I actually did not show you the phone. I just told you that here's my phone, but I did not show it to you. So those events are based on the knowledge that we know now are occurring simultaneously, and we have multiple realities. Okay, it's because of the things that you decide to do, or you did not decide to do. There could be another
Isn't that like
universe.
the isn't that like the Schrodinger's cat thing? Like the cat in the
Yeah, yeah,
box?
yeah. Schrodinger's
Like
cat, right?
whether or not it's dead or something?
Yeah, whether there's like a 50% chance that it is either dead or alive, right? So
Yeah, something
those
like that.
kinds of nerdy stuffs, I should say, but very interesting stuffs. I love those kinds of things. Um, it challenges our way of understanding things because we often think of events as like unilateral. Like it is it is this event that happened that is actually establishes reality, but based on our current knowledge, it's not. There are multiple realities that are occurring. They say occurring simultaneously. It's hard to even process that there's a universe that I'm the student. I'm living in US, and say Jeff is the teacher. Or even Grace is the teacher that she's living in the Philippines. So the our theory says that there's a universe that exists. It all depends on um, the multiple options of that we actually have. So there's another universe that I'm say a rocket scientist. They're in short infinite. They're infinite. They say again, it's just still a theory. There are infinite universe that are existing simultaneously. So it's really difficult to process that, to even think about that. But if you think about general relativity, it's just very counterintuitive. Like we do have different clocks, right? Relative to if we're moving or stationary. So it's really quite difficult to really understand nature, reality, even the concept of time. No one has ever really explained that in a very uh, intuitive way. So anyway, going back here, so that's conditional probability. And what do we do in conditional probabilities? If we are certain that the occurrence of B has something to do with the probability that A would occur, then we have to consider both their probabilities, right? Probability of A and B divided by probability of B. Of course, we cannot divide by probability of A. That's why you don't need to actually memorize this. It's easy to remember. If you're looking for the probability of A given the occurrence of B, now what is given? What is available to you? It is the probability of B, definitely. So what goes into the denominator would be the probability of B because it's given. Now, probability of A and B is something that you also know because you have stated that they are conditioned with each other. They are related with each other. So you know that there's interaction, there's intersection between them. So if you're not sure, say, Jeff, what if I'm not sure if they're independent or not? I have to compute for A intersection B. It's no problem. Why? Look at it. Look at the structure. If probability of A intersection B, right, is zero, what will you get? Zero divided by any non-zero number. So probability of A given B would be equal to uh, zero, right? It will be a null set in your numerator. So A given B would be equal to 0. So it tells you something. Well, if you want to identify probability of A, then it's just the marginal probability. You don't have to consider B because it doesn't exist. Okay. So yep. So that's conditional probability. And I think that there's further discussion here. Yeah, this is the discussion about the probability of the probability of rainy day and wearing umbrella. Yeah, let me see. Is it that? If we want to find the intersection probability, I don't know. This is a reverse thing. This is a reverse thing because what is given to us is probability of A given B. So from this formula, you just have to do transposition. If A intersection B is missing for some reason, um, or based on the structure of the problem, you can just multiply both sides by probability of B, right? I think I've shown it somewhere here. Yeah, there we go. You just have to multiply both sides by probability of B so that this would cancel and you have a probability of B multiplied to A given B, which is this part right here. But since probability of A given B is given, that is 40% in this case, right? That is the probability that you brought an umbrella given that it rained. So that's A given B times the probability of B, which is in this case the rainy day, 20%. So it's like um, a reverse of this, that you kind of want to identify that the intersection between the probability of rainy day and wearing an umbrella. So it must be a a low value, which is in this case 8%. I just played with this just to show you the how you would tweak the equation, how would you manipulate it? Just algebraic manipulation to isolate the one that you're looking for and utilize the one that you know of. You know of A given B, you definitely know probability of B, the marginal probability of B is given. So you're missing the intersection between a rainy day and wearing an umbrella. So of course you won't ask this type of question in your work, right? Unless again you're working as a teacher or you're a researcher on probability subjects. So we have this. We ended last time with conditional probabilities, and I'm not expecting you to immediately like have it on top of your head. I'm just opening this new avenue of knowledge about this subject. So it's completely fine to at first, um, I understand like maybe say 30% of it, 40%. There's no problem with that. But at least I've kickstarted your journey about this. So whenever you encounter in the future, yeah, we've gone through that, but I need to go back to the concept. So you know what to search for. You know what to research for. So this mathematics, I have a 90% confidence that you would forget that, but at least you've I've introduced to you the concepts. In the upcoming topics, this would not appear as exactly this way. What would appear would be the thinking, the application of the concept itself, not the formula. Okay? Like in regression analysis, say you're trying to understand sales. You want to identify what affects sales. Those are in terms of conditional probabilities, right? If you want to identify and predict what would be the sales if you say invest this amount of marketing dollars, then you're thinking about conditional probabilities. You're actually saying and assuming that marketing dollars has a positive effect on your sales, which is the reality, right? And you can think of so many other variables that are actually um, affecting it. So that prior knowledge that you know that when you invest in advertising, you would get more sales because you will get more reach. Uh, gives you that that ability to um, formulate this equation, this structure that would allow you to, in some degree of precision and accuracy, predict what could the corresponding sales for a given dollar, given amount of marketing dollars. So let's move on to joint distribution. So joint distribution is a statistical concept that refers to the probability distribution of two or more random variables. So what do we mean by random variables? You can think of so many things that would fall into the category of random variable. Your IQ is a random variable. It varies. Your scores, your salary, your age, those can be considered as random variables. And there are probability questions that can be asked related to it. So, what would be the probability that a person less than 50 or younger than 50 years old will get an average salary of, say, $100,000 per year? So, in order to answer that, you need to have data. You have to have those um, prior information that would give you. I'm speaking about the frequentist approach here, right? Given those information, you kind of have the not kinda, but you will have the all the information you needed in order to come up with that estimate of probability. Um, aside from that, you can think of so many other things like what would be the probability that a person who scored 75% in the midterm exams would get 90% in the final exams. So again, you'll be needing data, right? But without data, you will not be able to answer that. So those prior information would allow you to have an estimate of that probability, right? So let's have an example for joint distribution. So we'll have this example of rolling two dice. So consider the example of rolling two-sided dice. Each die has six faces, numbers from 1 to 6. Of course, that's the typical. But there's something called this tetrahedra or tetrahedron, which is like a die with I forgot how many faces it has, but it's definitely more than 6. So when both dice are rolled, there are a total of 6 times 6 or 36 outcomes, as each die is independent of the other. I want you to ask I want to ask you this question. Why is it 36? And why is it no, I've already included here the reason for 36. Why are they independent from each other? Say you got on the first die 3. Is it associated with any other value the other die. Like for example, based on experiment, whenever you get a 3, most of the time you will get a 6. Do we have that kind of characteristic when we toss two six-sided dice? Guys, are you still there? Are you still with me? Or is my what was my question clear? Again, let me repeat the question. You tossed the first die, you get a 3. You tossed another die, you get a 6. You observed in your data that that's always the case. Most of the time, you would observe that they are the values on the first die corresponds to like a factor, the factor of that number on the other side. Can you say that they are independent from each other? The answer is no, right? If you observe that when you toss it 1,000 times and a certain percentage, say 20% of the time, you observe that the corresponding outcome on the second die is like a factor of the results from the first die, then something's wrong. Maybe the dice are loaded to get that kind of outputs results. But in reality, we are assuming under normal conditions that dice, these two six-sided dice, should be independent from each other, right? So the event space would consist of 6 possible outcomes in each of the die. So that is in total, since they are independent from each other, we just get the A and B, right? Which is equal to 6 times 6, and that is 36. So there are in the universal event space, in the total set of possible outcomes, 36, 36 possible outcomes, since they are independent of each other. So we're defining here two random variables. Was that even clear, guys? Was that even clear? The thing that I just said. I want to know. Maybe a thumbs up would be would be sufficient for me to know that that was actually clear. Okay, you're suspiciously quiet, so I'm not sure if that was even clear. So again, just interrupt me if what I said is like doesn't make sense to you. So we'll be defining here these two um, events. Like X would be the outcome of first die, and Y would be for the second die. Now the joint distribution, as we define it, refers to the probability distribution of two or more random events or random variables, regardless if they're independent or not, right? So here, since we know that they are independent from each other, we can say that the probability mass function, those associated probabilities to each of the possible outcomes, would be generalized by p of x equal to small x and p of y equal to y. So those small x's, right, would be the actual outcomes that you have in each of the event space. So it could be 1, it could be 2, 3, 4, 5, or 6. And that would be the same for y because these are just uh, same die, right? So you have 1, 2, 3, 4, 5, 6 for the y. So specifically, we can ask a question such as, what is the probability that in the first die, it would turn up as 1? It would turn out as 1. So this value right here okay, refers to that first die, okay? And then what is the probability that y is equal to 1? Okay, what is the probability that 1 would turn out on the second die? So that is equal to 1 out of 36. The reason for that is we're just multiplying the marginal probabilities for the reason that they are independent from each other. So why you have a 136 in there, you might be wondering, right? Because they are independent from each other. The the probability of x given y is just equal to p of x, and probability of y given x is just equal to probability of y. So the marginal probabilities are what we will get, even if you look into the joint distribution of two or more independent uh, events. Okay, so that would be the same for any combinations of events that you can think of. It could be 1, 3, 1, 4, 4, 5, 4, 6, and so on. Dependent, then you just have to look into the marginal probabilities. Now, I put it in a table. So this is the joint distribution for each x and y. Now, I want to ask you, what is the marginal distribution for x and y? Can you identify the marginal probabilities for each x and y for these two um, dice? Anyone? Any volunteer? What is the marginal probability for x and what is the marginal probability of y? Anyone? Anyone who wants to try computing for the marginal probabilities?
Wait,
We just
isn't that just one?
um actually it's not one. It would be less than one for each.
Oh,
Like
for each, but I thought you
yeah,
mean combined.
yeah. Combined, it would be one because they are disjoint.
Yeah.
So we are certain, knowing that principle, that since they are disjoint, the sum of the probability of or I should not use the sigma here. We know that probability of x plus probability of y is equal to 1. This is your axiom 2, right? From the previous lesson. Now we are after with probability of x and probability of y from this example. From this example of tossing or rolling two 6-face dice. What could be the marginal probability of x and marginal probability of y? I'm assuming that they should be equal, right? Our assumption, okay, would be probability of x must be equal to probability of y. Why? Because they are just the same die, right? That has the same number of outputs. So thinking about naive probabilities, it will be part over total. So it's just the same die with the same number of possible outcomes. So they must be the same. But I'm after the actual value. What would be the marginal probabilities for each x and y? Any guess, guys? How did we define marginal probabilities? Let's go back to there and let's have an idea on what to do. We said that marginal probability is essentially basic probability, just the probability of a single event occurring, not worrying about anything. So with that idea, what could be the probability of x? Anyone? Okay, let me provide you the answer. I'll be providing the answer in a generic form and then proceed to the um, specific value. Okay, so we know that the event space for X. Why is it always doing that? Yes, sir. Maybe it's because of my mouse. Okay, so we know that the event space for X is 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6, right? Now, we said that the marginal probability is just the sum of the probabilities for each of the possible outcome in that event space. So in the universal space, we said that we could potentially have 36 possible outcomes because 6 possible outcomes on X, 6 possible outcomes on Y. Okay? Now, so this X could be equal, oh, always doing that. Hmm. Let me try again using this. So that would be this X would be equal to a certain value X pertaining to a specific outcome, right? It could be X equal to 1. What is the probability of that? What is the probability that a 1 would turn up when you roll it? When you roll a die? When you roll the two 6-face die. Any answers, guys? Maybe the table would help you to go back to the table. No guesses, guys?
So 1/36
Exactly.
for
1 over
one.
36. So we are referring to X equal to 1 here, and we're certain that if that's the case, you have a 1 out of 36, right? So it's also the case when you have a P of Y equal to 1, a P of X equal to 1, a P of Y equal to 1. Both will be 1 out of 36. So that's the answer. And you can repeat that. You can repeat that for um for each value, each potential values of X and Y, right? Do you follow? Or maybe I should let's have a quick break. Maybe I think John is not present today, so I think I can go over time a bit. So let's have a maybe a 5 or 10 minute break. But I'll still show you this table, okay? And while you are refreshing, maybe you can take a look at it, and maybe it would reveal the pattern to you. Okay? So let's be back after 10 minutes. So at 9:40 on my time. Okay, I'm back. Are you there now, guys? So, yep. So going back to our question here, what is the marginal probability of x, and what is the marginal probability of y? Start with the fresh slide here. Um, P of x equal to x, P of y equal to y. Any guesses, guys? Based on this table, you can easily see the marginal probabilities for each. When we say marginal probability, we disregard every other thing and just focus on uh, that single event space that we have. If it's x, it's x. So how many possible events do you have in your x? How many possible results? There are 6, right? If you count all the possible values, it would be x equal to 1, x equal to 2, x equal to 3, x equal to 4, x equal to 5, x equal to 6. That's what we are saying when we write p of x equal to smaller x. The smaller x could be equal to 1, could be equal to 2, and so on up to the last, which is equal to 6. Now, if you sum up those probabilities, right, or not probabilities, but number of events, number of possible events for x, or number of possible values, you will get 6. And now, what should go in the denominator? Since you're considering here joint distribution, instead of just looking into the event space of only x, you'll also consider y. So that would be 6 out of 36. So it's simply summing up all these values: 1, 2, 3, 4, 5, 6. So you have p of x, the marginal probability of x, equal to 6 out of 36, right? Which is equal to 1 out of 6 in a simplified form. Now it's almost the same. It's actually totally the same as with y. So you see probability of x equal to, or the marginal probability of x is just the same, right? Even if you considered it independently, okay? Because if you can remember, we have defined the marginal probability of x before, and say observing any value that x can assume, either 1, 2, 3, or any value in between 1 to 6 will be equal to 1 over 6, right? And for y, it would still be the same because it's just the same die. We just denoted a different a letter to it. So that would also be equal to 1 over 6, right? And you might be wondering, Jeff, if the marginal probabilities of both x and y are the same, 1 out of 6, then if we merge them together, isn't it not less, or isn't it not equal to 1, which is supposedly our check for whether this is a valid probability, whether if we got the correct probabilities. Now, the computation for the total probability is different in this case because they are independent from each other. So we have to consider all of the possible combinations that they can assume, right? You can get not only one x and one y, you can have one x and two y, right? X equal to 1, y equal to 2. So all those combinations together, if you sum them up, right? If you add this would be 6 out of 36. 6 out of 36. 6 out of 36. So it will be 6 times 6 over 36, right? And that is just equal to what we're looking for. That is 36 over 36, which is equal to 1. Do you follow? Do you follow, guys? Did that make any sense? That we have to consider all other combinations of them. Y could be 1, X could be 2, X could be 1, Y could be 2. So all of those possibilities um, considered all together to complete that set of events that you can possibly get with the joint distribution of X and Y when you roll a two-sided, or at a when you roll two six-faced die or dice. So that's how you get this is the joint distribution, this is the marginal distribution, and this is the total probability when you consider all of the combinations in which P of X equal to small x and Y equal to small y, not necessarily Y equal to 1 and X equal to 1. So if that's the case that you're looking at, then you have this, in which in every roll you have 2/6 or 1/3 chance of getting the values that are the same, uh, values that are the same. So that is 1 1 2 2 3 3 4 4 5 5 6 6. Okay. Wonder if I did a good job of actually explaining that thing. Any questions, guys? Was it even intuitive or clear? Okay, so I think it takes time to really process that, and maybe additional examples would do. So I'll be asking John to give you more examples and hands on during the lab for it. Why is it not removing the? Okay, it's not changing the logo. Anyway, so that's the answer for this one. And now we are down to the last topic in this lecture about the basics of probability. Now we have the base rule. So the base rule is the foundation of one of the main branches of statistics. So statistics is there are two schools of thought rather for statistics. One is the frequentist approach, and the other one is the Bayesian approach. So the foundation of Bayesian approach, Bayesian statistics, is from this Bayes rule. So Bayes, he is a priest, I think around 18th century, um, and he was one of the most prominent statistician of that time. Let me give you the information about Bay. Um, I think his first name is Thomas. Yeah, Thomas Bayes. So this Bayes theorem that he developed revolutionized our thinking about probabilities. So it is basically our knowledge about prior knowledge about the probability of an occurrence of something is changed based on a related event that has happened. So it allows us to update our probabilities. So that's what we have with the Bayes rule or Bayes theorem. And I wonder if they have a picture of Thomas Bayes in here. Um, I think none. Yeah, you can also find here um, Okay, the derivation of Bayes' rule. So notice both of this. The difference is just the denominator. You both need the intersection, right? But the intersection can be expressed in a different manner, so that you can have this structure of the Bayes rule. This is also applied the same principle as when you have P of B given the occurrence of A supposedly, right? So you'll just have in your numerator the reverse, A given B, and this time it would be probability of B over probability of A. So basically, we're updating this probability of B that we have a prior knowledge of its probability by taking into consideration the occurrence of A. Okay, the occurrence of A in here. So this allows us to update our estimates of probabilities for B. So sometimes it gets significantly lower, sometimes it's significantly higher based on how the well, it's a case-to-case basis, but essentially that's what Bayes rule is all about. It's about updating uh, your prior probabilities based on the information um, that's in hand or on hand. So let's see an example for the Bayes rule. I'll not go over to the like the main derivation of this thing because you don't need it. We have to focus more on how can we use it, right? So Bayes rule, let me go over this. Bayes rule, also known as Bayes theorem, is a fundamental concept in probability theory and statistics. It describes how to update the probabilities of hypotheses when given new evidence. Bayes rule is especially useful in various fields such as medicine, finance, and machine learning. So think about this way. Historically, I say that my passing rate, okay, the passing rate in my classes is around 80%. And given that the passing rate on the previous class was just 40%, what is then now my new passing rate? How does the this new information about the previous um, class that ended update my prior probability, my hypothesis about my passing rate? So that's where we kind of make use of base probability or base theorem or base rule in order to update the probability. Okay, our prior knowledge of the probability of that event. In this case, my passing rate. Now, mathematically speaking, base rule is not that much complicated, right? Since we are now knowledgeable about the actions of probability, we know what this means, right? Probability of A rather given B. So we are assuming that they are related because if not, then the occurrence of B doesn't really affect the probability of A. So there must be a connection between the two. So that's something that you have to remember. Now, notice that in our denominator, we have probability of B given A. So basically, we have a prior knowledge of A. We have a prior knowledge about the probability of A. That's why we have it in here. And we are updating our uh, our thinking about that probability, about that prior probability of A, given that we have new information coming in the form of the occurrence of P. Okay, so we are dividing that by the marginal probability of B at the denominator, which is basically um, straightforward computation, right? So let's see that in action. Let's see. Probably this is one of the most counterintuitive concept in probability. Okay, one of the so many things that you would encounter, but after careful thinking, after deeper analysis, you would realize that it makes perfect sense to have the prior probability be adjusted by the fresh information that's coming in. Okay, so Bayes' rule helps us to update our beliefs based on new evidence. So in my example before, my belief that I have a passing rate of 80% would now be challenged, would now be changed by this fresh information that my last class only has 40% probability or 40% passing rate. So if I would market my class, it would now be erroneous to say that I still have 80% of 80% success in my classes, or 80% of my classes would be passing. So it allows us to start with an initial belief. Okay, that is in this case, if you go back to this formula, your initial belief here would be P of A, right? And adjust this belief when new evidence is observed. Okay, it would be the occurrence of B. Okay, the event that is associated to your event A. Now let's have an example here. Consider a scenario where a doctor is diagnosing a disease. So I think Grace can relate so much with this. So let's have two events. Event A represent the event that the patient has the disease. Okay, that's the event. And B represent the event that patient tests positive for the disease. Because there's a possibility of B prime or B bar. That is the event that a patient tests negative for the disease, even though the patient has the disease, right? That's called false positivity. It's false positive, or rather, I should say false negative. The test says you're negative of the disease, but in reality, you actually have the disease. The other way around is the test says negative, but you actually have the disease. That's false negativity. Okay, do you follow, guys? This part. There's also another event called a bar or a complement in which you don't have the disease, but the test tells you otherwise. You don't have the disease, but the test says you're positive. Those are the different errors. Those are the different problems that you would encounter in this field, and we try to minimize that, right? And we also want to have a glimpse of what could be the probability that you actually tested positive, given that you really have the disease. So in that structure, you would see this A given B kind of thing. You have that given information. There's an association with those two events, right? Now let's define some of the things that we need to apply Bayes' rule. So we have P of A. P of A is the prior probability that a patient has the disease. That's our notion. That's the prior information that we have. The person has a disease. probability of B given A is the probability that the patient tests positive. That's what we have in here, right? It tested positive given that they have the disease. This is the true positive rate. This is what we want. This is what we want to be very high. You have the disease and you tested for positive. Okay, it's bad if you have a high or very low true positivity rate because what you do with that is um you are having more false positives, right? You're saying that a person has a disease even though they don't have. Okay, so there should be a balance on the true positivity as well as this third one, which is the false positivity rate. So the false positivity rate tells that the probability that the patient tests positive, given that they do not have the disease. Okay, so in this part we want it to be low, right? We want the false positivity rate to be um, uh, as low as possible. Again, the probability that the patient tests positive, given that they do not have the disease. Imagine you're prescribing medicine, thinking that they are positive, that they have that, thinking that they actually have the disease, but in reality, they don't have. So you're doing more harm through the medication, um, because in reality they don't have the disease, and aside from the cost, also cost consideration. Then we have A complement, which is A bar. This is just the inverse of this. So the prior probability that a patient does not have the disease. So all of those are needed information for us to apply Bayes rule. Now, what is our goal? Our goal is find the probability that a patient has the disease given a positive test result. Okay, given a positive test result. So if you would construct that, you would go back to the definition of the events. So when it is that a patient has the disease, that is your P of A. Given a test result that is positive, that is your B. So basically what we're finding here is P of A given B, right? If you go back to this given information, that is P of A given B. That is what we're looking for. Now that is specifically structured to follow the Bayes rule that we have in here. So P of A given B needs the following ingredients, needs the following parts. Okay, P of B given A. That is the probability that the test is positive given the person has a disease. Then you have the probability that the person has the disease in the form of P of A, and P of B would be the probability that the person tested positive. Okay. Now, as you might be thinking, let me see the chat box. Hey Jeff, I'll have to be on the road now. So okay, no worries, no worries. Thanks for letting me know, Jeff. So going back here, okay. So having this on our mind, this structure of the Bayes rule, go back to our given. So we have P of A, which is nice. It's part of our numerator. But we don't have P of B, right? We don't have P of B here. We do have other stuffs here that are in a way related to P of B. So we can extract P of B from it. But that's the missing part, right? We have P of B given A, the probability that the patient tests positive given that they have the disease, which is the true positivity rate. That is part of the numerator. So what's lacking is this P of B. Now that's the main challenge, okay? Because we will be applying a concept that we haven't really went through that I will just introduce to you, which is a very monumental concept in probability. That is called law of total probability. So the law of total probability states that you can extract, say, a given probability, say a marginal probability of B, given other parts. So let me show to you the main definition of law of probability, uh, law of total probability. This is a very useful law in probability that would allow us to generate those marginal probabilities that we actually need in order to apply the Bayes rule. Um, so this is this is how we define it normally. If B1, B2, B3 are partition of the sample space, meaning if there's a partition on the universal event space, then we can compute for the probability of event A such as this. So by looking into individual parts, we can actually compute for the marginal probabilities of either A or B. Now, if for example here, I'm thinking of a better example. Now, maybe let's go back to the slides because I have there something that is yeah, here we go. Now, what we're lacking here is the probability of B. This is okay. This is okay. But this and this, what do we mean by those? P of B given a bar is the inverse of this, right? And the inverse of this is actually a bar. In short, if we're only speaking of two events, A and B, we have all the partitions that form the total probability of those two events. Okay? We have the prior probability and we have the complement of that probability. This is the prior probability of A. This is the complement of A. This is the prior probability of B given A. This is the complement of that prior probability. That is when we don't have or rather not we don't have, but when we consider the complement of A. This is the probability of B when you consider the complement of A. So what we're lacking with is just the marginal probability of B, and that's how we will compute it through knowing that we have the individual parts of what constitute the entirety of the probabilities of this A and B events. Okay, so knowing that we have all the partitions that we need, we can proceed to this. Okay, so these are just um, assumptions. What if the P of A is 0.01? Okay, the probability of that disease, of getting that disease is just 1%. And I'm not, let me go back to, okay. The probability that the test is fairly accurate would be the true positivity rate is 99%, which is a pretty accurate, right? A pretty accurate test when you have a 99% true positivity rate. And a false positivity rate of very low, 5%. So by standard, we know that these figures are indeed accurate, right? They're good in terms of standards, 99% and 5% false positivity rate. We can live with that, okay? There will be no issues. But what we're really after with is how can the prior probability be updated by the existence or the occurrence of a particular event? In this case, the occurrence of that rare disease, given that a positivity test has been, or a positive test has been observed. So let's structure it and apply the Bayes rule to it. Okay. So going back to the formula, we're still missing P of B. Okay. Probability that a patient tests positive for the disease. And this part right here is actually the application of law of total probability. probability of B given A times probability of A plus probability of B, A complement times A probability of A complement. So you have two partitions in there. And what you're lacking there, okay, would be probability of B. So using that idea that um, you can you can put the event space in different partitions, right? Looking at the definition of total probability here, we can treat the event spaces as, where is it? Having partitions. Maybe we can look for a better discussion of that. Let me see. Maybe this one is way better than the first one. Hmm. Yeah, this one is way better. I mean, this is very intuitive. This is very intuitive in terms of explaining law of total probability because it has a visual guide. So yeah, B plus B complement, we know that it corresponds to the entirety, right? If we consider the event space, the event space will just be equal to B plus B complement. And we know that this is equal to 1. This entirety, this entire rectangular, uh, if you think about that in terms of probability, the area of that square is actually equal to 1. Now, here we see that how can we take the probability of A, this part right here. So it's similar to our goal currently of getting the probability of B. So we are saying that, okay, you need first the intersection. Okay, you need the intersection of A and B, right? Plus the intersection of A and its in the complement of B. What is B complement in this case? Guys, B complement is all that is yellow. And if this A corresponds to this circle, this A intersection B complement is all the content of the circle that is yellow. So this part right here corresponds to A intersection B complement. And if you add it to this A intersection B, the commonality between A and that of B, you'll get the totality of A. So this is exactly the idea that since we know the total, right, and we can partition it, partition of B, partition of A, partition of B complement, then we can solve the other parts that are missing. It's like the analogy could be like completing a puzzle, right? If you know that the puzzle is missing like certain number of pieces, then it would be easier for you to identify where those pieces must be um, must be allocated or must be um, assigned to. So it's just the basic concept. Maybe at this point, this way, it's much easier to visualize. Just see, okay, this portion is what we're looking for. This circle. What are the compositions of it? There's a part that is belonging to B complement, but also there's a part that is belonging to B, right? So that A is in between the two partitions. And A intersection B would be this green part, or I'm not sure if it's green or blue. And this A intersection B complement, that part that is not contained on B but is contained in A, will be this all that is yellow, right? So A is in between the two partitions. And that's how we can get the B here. So if we go back to our computation of the Bayes rule, it actually follows the same principle, right? You would be looking into the probability of B given A times the probability of A plus probability of B given A complement or A bar times probability of A bar. So basically what's missing would be this probability of B that we're needing to complete the formula for the Bayes rule, the denominator, and that's how you implement, in this case, the law of total probability to solve for it, given the set of information that we have. Okay? This completes the ingredients for you to get that partition in your event space corresponding to the probability of B. And we know all of those information. We know that P of B given A is the probability that a test results positive given that the person actually has the disease. That is 99% our true positivity rate. And that probability of A, that the probability that you will get that rare disease is just 1%, right? Those are given information, right? So we multiply both of them plus, okay, plus 0.05, which is our false positivity rate, times 0.99. So if you add them all together, what you would be missing in order to actually get the P of the event space equal to 1 would be P of B, which is just equal to 0.00594, right? So the probability of B is just 0.0594, and we can plug it in. This value can be now plugged in to the formula of the Bayes rule. Okay, the formula of this Bayes rule, so that we can update our prior probability for A given the occurrence of B. So let's see. So we can now apply the Bayes rule to update our prior probability for A given the occurrence of B, since we have now all the parts of the equation. Probability that the test is positive given that the person has the disease times the probability of contracting that disease, which is 0.01, divided by probability of um, B, which is probability of having a positive test. Okay, probability of having a positive test. So we can now see that probability of A given B, okay, the probability that you have a rare disease given that the test is positive is only 17% or 16.67. Now, why is that low? Why is that low? It's very surprising, right? Because earlier we have our prior probability for A, where is it? Our prior probability for a positive test, given that the person has a disease, is actually 99%. That's our assumption. We assume that our test is that accurate, but we're not forgetting some stuffs here. But we are forgetting some realities here that we need to consider. So let's see. Did you notice something? This result might seem counterintuitive at first because the test is quite accurate. 99% true positivity rate and 0.05 false positivity rate. However, since the disease is rare, okay, since the disease is rare, even a highly accurate test will yield a significant number of false positives. And it's very likely to do that. right? If the disease is really rare, then it is likely for you or for that test to yield more false positives, a number of false positives, right? Even if it's 99%, it has 99% true positivity rate. It would still yield a number of um, false positives because of the fact that the disease is rare. Okay, so Bayes' rule helps us to account for this. Okay, helps us to account for the fact that the disease is rare, so that we can update. Okay, our prior prior understanding of the probability or the assessment of likelihood of having a disease given a positive test result has occurred. That's why doctors they do follow up, checkups, right? They have verifications. They don't really um if a disease is rare, they do follow up checkups. They do um how do you call that, Grace? You're working in the um medicine or in the health industry.
No, follow-ups is correct. Yeah.
Follow up is correct. If for example that disease is really very rare, they would be they would be questioning whether the what the test, if
Oh,
it's positive.
it's not a follow-up. Follow-up is like like after you've been diagnosed, like or
Mhm.
after say you've been diagnosed and they give you medication. So a follow-up would be like the appointment after to see how the medication is working. What
Okay.
you're talking about, they would say they would do further workup to confirm.
Further workup, yeah.
Yeah.
If yeah, let's consider this just to make sense of what happened here. Let's say that a specific disease affects 1 in a billion people. 1 in a billion people. Even how accurate, how sensitive, and how high the specificity of your test is, it would still leave a doubt because of its rarity. Okay, you would still leave a doubt because you know that it could be just a false positive because it's very rare, right? So assuming that since we have a 99% true positivity rate, we are 99% sure that that person actually have a disease. It's totally wrong, right? It's totally
I
wrong.
think I
Mm,
think nowadays the next step would be to actually do a genetic testing if it is
exactly.
genetically encoded, you know. They
Further
would say let's
further
test. Yeah.
examination would be needed if it's really a rare disease. However, let's take another example in which it's not really a rare disease. It's a common disease. So there would be more there would be less false positive, right? There would be less false positive in that sense because it's more common. Like if it's affecting, like say ADHD is like affecting a significant portion of the population, right? So since it's not rare, then the prior information, the prior probability would not be that much affected if we consider the fact that like 60% would be the probability that you'll be you will be identified as a positive for um, ADHD, given that you actually have a ADHD. So that's why base rule is important. It gives us a way to update our a prior knowledge about the odds and the likelihood given new sets of information that are coming in. Okay, so yep. It might require us more examples, but due to lack of time, maybe we should consider it maybe during labs. But base rule is one of the monumental um, things that has been developed in the early 18th century that even until now, after several hundreds of years, it's still being used in machine learning, in so many fields. So imagine one person was able to develop develop this concept. Really a genius. So that ends our discussion for the basics of probability. But again, we have only scratched its surface. Maybe there are still 96% of the things that we haven't talked about, because this subject really needs mm, years for you to really master it. And but we don't have to do it because this is a boot camp. um, we'll just use that knowledge. We'll be referring back to it. For example, when we discussing regression with categorical variables, what do we mean by subsectioning the individual effects of um, these different groups to your target variable? Like the thing that I showed you last meeting, we modeled this breakout strength of concrete that is mixed with bamboo fibers. So those subsections, you would see those partitions that actually um, have different effects on the breakout strength. It could be at some formulation, it would help in increasing the breakout strength. But if you look into other formulation, a much higher formulation, then the breakout strength tends to be weaker. Okay, so those kinds of things all boils down to the foundation, these things that we're talking about. So what do we expect next meeting on Saturday? Um, we'll have a discussion about discrete and continuous distribution. Those distributions are what you use when you compute for statistics, like t distribution for t statistics. Those are like the sources of the probabilities that you generate from each of the methods that we talked about before. F test for ANOVA, right? F distribution. So F distribution is the one that you get the p values from for a from an analysis of variance test. Regression analysis both uh, regression analysis gets both t t statistic and f statistic. T statistic for identifying if a certain predictor is significant. We use t-test there, and for the overall model fit, we look into f statistic or f distribution. So that's what we have in the next session. Still a bit theoretical, but I'm not really going deeper. If you will be, this is how it looks. Let me just show it to you. This is how it looks in like very theoretical discussion of probability. Hmm, let me just show to you how it looks like. Um, yeah, there we go. This one. So this is the one of the books that I used during the time that I was teaching at the university, and when I studied my master's in statistics. This is Mood, Grable, and Bose probability theory. Look how different it is. It is like purely hieroglyphics in a sense. Oh, it has only limited preview. Oh, it doesn't help. Let me get another one. I think I have a copy in my drive. And I'll be sharing this to you if you want to dive in deeper to the um, core of statistics. Yeah, this looks like this. The things that we're discussing in a um, purely mathematical percep pers perspective, it looks something like this. Wait, let's look for. Yeah, this is the base rule. As you can see, the notation is almost the same, but it's presented in a different way, much different way. This is the law of total probability that we talked about, but in our case, it's quite different because we considered P of B, and we have the information about P of B given A, P of A, and P of B given A complement and P of A complement. It's still the same thing. It's still the partitions of the event space, and it would allow us to use those information to actually solve for the missing part, like a piece of how do you call that, puzzle. And this is the probability axioms that we talked about. This is the bound, the lower bound. This is the upper bound. This is the when you sum up the valid probabilities, it would be equal to one, and so on. This is the definition of a conditional probability, the independence idea. And if we go to the like most complicated part of it, you can actually see the theoretical underpinnings of like what do you mean by random sample or sample statistics, or what do you mean by the average or the mean. So mean is just expected value, and it is like the expected expectation of a random variable. So those kinds of things. I'll be putting this also in the module, but yeah, you have to review your calculus in order to understand some parts of the advanced stuffs for this one. So we sketched this surface, joint distribution, but we haven't discussed cumulative distribution because I think it's not really needed for your case. So that's what we have for today, and hopefully we can finish all of the intended topics this week on Saturday. And on Monday, that will be our last day for probability because I think John was able to cover all of the methods that are in our syllabus and even beyond that. And I'm very happy with it. We discussed non-parametric tests, which is not really part of the curriculum. So that's good. You have a wider knowledge about the method, like alternatives. So I'll be giving your exam starting on Wednesday. So Wednesday to Saturday will be your exam. So your exam would contain medical information, okay? Medical data that consists of around 40 variables, and it is a very messy data. So I'll be giving you all the leeways that you need, whether you want to clean that data using Excel or you want to test your skill using Python in order to do the data cleaning. But with analysis, I would be expecting you to use Python. You can use AI. There's nothing wrong about it. Just make sure that if there are parts in there that you're not sure on what is it for, ask Gemini or ChatGPT on what does that thing do, just to um, be be full just have to just to have full understanding if you have the correct thing that you want. So there will be structured questions that you need to answer. Okay, and after that we'll be proceeding to Power BI. Power BI is just a bonus to you. Bonus to you. It would be very easy. I'm using Power BI at work as a technical product manager. So I'll be showing to you the dashboards that we're using in the company. I'll be tweaking some information for confidentiality. So, yep, that's all. Thank you very much, Grace, Hasiba, Jeff. I know it's a very dense, complicated topic. I'm very happy, and I, I, I'm very happy that you're here, you're present. Let me look at the chat box. Hasiba says, "Do we have the mods?" I'll be uploading it now. Okay, after this class, I'll be uploading this finished module in Canvas. Apologies, Hasiba. Um, yeah, yeah. Sorry about the delay. So thanks, guys. Bye bye. Have a great one.
Thank you. Bye. Good night.